Okay, well, we hit 1,000 people, so I think it's officially a party. So this is totally weird. I'm used to talking to you through this channel, and you're used to seeing me, I guess. But usually there's this time lag, like you're in my future, I'm in your past. This is the first time I think I've talked to you in the present. Or is the present an illusion? I'm not sure. But I need to welcome you to my home, my living room. Some of you, most of you probably, you early guys have seen my living room before. You've hung out here for the past few episodes. This is the lockdown studio, but having you here right now is extra exciting, so welcome. Normally I would offer you a drink, but there's 1.4 thousand of you and we don't have that technology yet. So fetch yourself a drink, please. I already did. And here's to you. This is a Negroni, by the way. I don't know if any of you follow viral cocktail memes, but recently Stanley Tucci, the great actor, made the rounds for this little footage of him making a Negroni in his caravan or whatever on shoot, and everyone's like, "Oh my god, the perfect Negroni." I beg to differ. Stanley used too much gin. He did use exactly the right type of vermouth, but he shook rather than stirred. I'll probably show you guys how to make the actual perfect Negroni. There's a little secret. I don't know if I'll have time today, but for now, here's to you. That is delicious. So this is the first Space-Time live stream. I don't know why we thought this was a good idea, except for the fact that I am locked in this apartment, and it seems like a time to do crazy stuff. So how is this going to work? Well, it's going to work how it always works when we have nearly 2,000 people in a room together. We're going to talk about whatever we want to talk about. We're going to talk about space stuff, physics stuff, but we're also going to talk about really anything else that we get to. You guys can put your questions in here, as I see you are. We also asked for questions, pre-questions in the community tab on the channel, and we'll select a few of those questions. And we also have some questions from the Discord channel. Okay, so the Discord channel, like if you think this is fun, the Discord channel is internet space talk, physics talk 24/7. You do need to be a Patreon subscriber, but lowest tier, a couple bucks a month, grants you access, and there are people much smarter than me there, so it's the place to get your physics questions answered. My microphone seems to have popped my shirt button. That's unseemly. Okay, so there's lots of types of questions we could go through. I'm going to just start by talking about the show, and we'll get into some science and we'll get into some other stuff as we go along, as it feels right. So, space-time, we're, what are we, 5 years in, 6 years in? We've done, I believe it's over 240 episodes now. I don't think we ever thought that would be possible, starting a show with such a ostensibly narrow field of interest, hardcore physics and astrophysics. But it turns out that the universe is big and deep, and I cannot think of an end to topics that I want to talk about. That said, we have some very cool stuff coming up. We just shot an episode on a cool topic, the luminiferous ether. I can now say that word. It took many takes to be able to say it reliably. The luminiferous ether, which is this archaic notion about the medium through which light propagates, and the death of the idea in the late 1900s, late 1800s, ushered in the era of relativity and quantum physics. And this is kind of, Astro 101, except for the fact that I dearly love these old wrong theories. I think they're so colorful and cool. The one electron universe of John Archibald Wheeler, or Paul Dirac's electron sea. I'm just a huge fan of wrong old science that actually pushed the science forward. So I'm really excited for that episode. I think it came out really well. It is, of course, right here in the apartment. We're working super hard with our resident quantum physicist, Graham Gossell, on a topic about electroweak unification. Okay, so one for the hardcore, but I think it's going to be very beautiful because it really, I think, reveals how it is that the forces of nature, our notion of what a force is, emerges from the simple concept of asymmetry. So with these super hard ones, we struggle for weeks and weeks to get them right, because it's tough doing quantum field theory in 10 to 12 minutes, but it's really coming together nicely. So those are two things that I'm really looking forward to, and maybe I can give you some more hints about what we have going on down the line as I move through some of your questions, which I should do right now. So I'm going to jump into a couple of questions that we got from the Discord and from the community channel. Let's see. We'll start with questions about the show, and then we'll jump into some science. Okay, so Tutul from the Discord asks, how many hours of work do you put into an average video? Well, the answer for that is, me personally, it depends massively on the video. If it's something I know well, then I can write a script in a few hours. But if it's something like gauge theory and electroweak symmetry breaking, then working hard with a quantum physicist, it can take us many hours, but scattered over weeks. It's really hard to even enumerate them, and presumably dreaming about the stuff as well. I was certainly dreaming about quantum loop gravity and string theory when we were writing those episodes. So it varies massively, but the show isn't me. I do the talky part, and I also I write most of the episodes with essential help in some cases, but the show wouldn't be the show if it wasn't very beautifully animated. And currently we have an amazing animation team, actually led by Leo in Brazil. Details are in every credit, and these guys work hard with me as I try to somehow articulate what I think things should look like and what's scientifically accurate, but they also put an incredible amount of their own artistic ability into it. Andrew Kornhaber of Kornhaber Brown is the producer of the show. He directs the show, and until the lockdown, he shot the show as well. But these days, my partner Bahar, who you may meet, sort of takes on the role of assistant director and camera, and so it's a team of a few people, and I mean, in the end, we do one show a week, so it takes us that much time. I also try to do other things, and there are some questions about that, so I'll hopefully get to those as well. Um, let's see. So I think I just answered Emily also from the Discord's question. How do we develop the graphics and imagery? Really, it's a collaborative thing, and we iterate. And I send bad mock-up graphics, and the graphics team produces beautiful graphics. Is the graphics team educated in physics? Emily asks. The answer is they're becoming increasingly educated in physics, and the main thing is that they are just very smart. And so, you know, they get it very quickly. So, you know, that's the show. It's a labor of love, and you know, we'll keep doing it as long as we can. But honestly, it's your support and the fact that you know, PBS sees your extreme enthusiasm for us doing this, that ensures that we keep being able to do so. Let's talk about science, because this, you know, really this is a science show and this is what we all care about. So I'm gonna, let's see, maybe I'll take a question from the audience if I can locate my browser. You guys are flicking through so fast. Favorite Mass Effect game? There were multiple Mass Effect questions actually, including. Let me see. Oh, we'll get to that later. Let's talk science for now. Matt, if you're a physicist, why do I feel chemistry between us? I guess that's science. What's your deal, man? These are unanswerable questions. My favorite type of sandwich. I don't know. I really like a great tuna melt. I make a great tuna melt. Why is the speed of light what it is? That's a deep one. So this question is one I asked also coming into thinking about physics and becoming a physicist. And I guess the shorter answer is it's because we define it to be what it is. We define the speed of light to be what it is because we define the length of the second, and we define, you know, the meter, and so we end up with a certain number of meters per second. But I like to think of the speed of light as the speed of causality. If you choose to think of the universe as an ensemble of little elements, maybe they're pieces of space, maybe there's something from which space emerges but aren't space themselves, but they talk to each other at a certain rate. Okay, a change in one part of the universe can lead to a change in the adjacent part of the universe, and so on and so on and so on. And that rate of communication, that rate of causal influence, propagates at the speed of light. It's really the speed of information, okay, the speed of causality. And it doesn't necessarily have a fundamental speed in itself. What's fundamental is that it can happen at all. The idea of the speed of light comes into it when we think about sort of the size scale of the observer, the size scale of a human being relative to that propagation. Okay, so how many little propagating blips does it take for that propagation to, for example, traverse, you know, the size of my head? Okay, and so the speed of light is what it is because it's a statement about our scale relative to these fundamental tiny scales. Okay, I see an episode here. I think this is going to be a great episode at some point. But you know, physicists like to set the speed of light as being dimensionless and set it equal to 1. Which is totally reasonable if for the right definition of, you know, length and time. And so speeding up the speed of light or slowing it down, it's not even clear what that would mean for the rest of the universe. So the idea of an object in space, or a most fundamental element of space, influencing the next element and influencing the next element, and so patterns emerging, and so all this amazing emergent structure appearing in the universe. This notion is sometimes referred to as the idea of cellular automata. Okay, so the idea that you can think of a simple set of rules for an element of space interacting with neighboring elements, and that will lead to this emergent complex structure. Okay, and you know, perhaps the most famous example of that is Conway's Game of Life, which you've all seen it, I think, if not Google it. But by the way, John Conway, who was the great mathematician who came up with the Game of Life, recently passed away. So R.I.P. to John Conway, sadly of COVID-19. So the idea of cellular automata, I bring it up because it was a question from our community tab. Jake Montgomery asks, what do I think of Stephen Wolfram's new idea for a theory of everything? Okay, so again, this one has been all over the news recently, mostly because I think Stephen Wolfram blasted it over the media. But this is the theory is a type of cellular automaton theory in which these kind of connected structures have these rules by which they can evolve, and then you can produce all sorts of geometries, and according to Stephen Wolfram, you can basically recover the laws of physics and our universe from this notion of a cellular automata. So what do I think of it? Well, you know, I skimmed the 450-page paper, which means I certainly didn't read the 450-page paper, but I got a sense of the fundamentals of the notion, not enough to be able to say whether Wolfram's claim is right, that it can recover special relativity, general relativity, quantum field theory, and all this stuff. So I maybe the best thing is for me to cede this answer to someone who would know much better than me. Now, this is hearsay. I got this secondhand. A friend of mine is a surfing buddy of Garrett Lissy, who some of you will know for his, is it called The Incredibly Simple Theory of Everything? There's a TED Talk. It's an E8 theory for particle physics, and Garrett Lissy found, this is hearsay, so Garrett Lissy can happily deny this. It may not be the case, but it seems reasonable to me that Wolfram's notion is superb and majestic, but probably a waste of time. And to understand why, well, I think this is all. In general, I'm fascinated by cellular automata, so I may do an episode on this. In fact, I think I must. In Wolfram's idea, essentially you can produce these emerging structures of space and time from these simple evolving rules, you know, like Conway's Game of Life. But the problem is that there's no way to predict what universe will emerge from a given set of rules. And Wolfram calls this concept irreducible computability, which is to say, you can't use this set of rules to project whether this particular set of rules will generate a universe of 3 dimensions that has this particular set of laws for gravity, for particles, whatever. The only way to learn this, to learn what universe emerges, is to run a full universe simulation and see what universe emerges. Okay, and so, you know, in the sense of it potentially being a waste of time, it may not ever be testable. That said, some of the greats in physics have turned to these ideas of cellular automata. Okay, Gerard de Hooft, the great string theorist, great everything physicist, published a cellular automata paper, not necessarily saying that it was right, but just to show that it was possible. The idea that you can have rules that take simple bits of information and generate something complex. And John Archibald Wheeler also, with his notion of it from bit, okay, and complexity and the idea of physicality emerging from simple, more like informational components. There's something compelling there. Okay, so I wouldn't discard Wolfram's idea just yet, but he probably should get that thing peer reviewed, which he has not, and so it's certainly hard to judge, me being a lowly astrophysicist. Okay, so I'm going to turn to another question from there's a couple of good questions on conservation laws. So Michael from the community tab asks if I can describe how dark energy and evaporating black holes with virtual particles do not violate conservation laws. So let's start with dark energy, because Thomas Lopez also asks if we can explain what happens to the energy of photons that are redshifted, okay, and the redshift of gravitational waves. What happens to that energy? Well, so the answer is there are a couple of schools of thought on this regarding energy not being conserved in an expanding universe. So school of thought number one is that the loss of the energy of those photons and the creation of new dark energy in an accelerating, expanding universe actually does violate the conservation of energy, and that's fine. And the reason that could be fine is that conservation of energy is specifically valid for time-symmetric systems. Okay, so we did an episode on Emmy Noether's theorem, which reveals why quantities are conserved at all, and it's when there's a symmetric quantity. Okay, so if the laws of physics work the same going forwards or backwards, or work the same from one time versus another time in the universe, then it's a relatively simple calculation shows that we must have this conserved quantity called energy. Now, in an expanding universe, time is not symmetric. If you reverse the expansion, then the universe is getting smaller rather than larger. Okay, so the space itself is changing. And if you look at different times in the universe, they're not symmetric. Okay, so there's change. And with that change, we lose the ability to say that energy is conserved. Now, it may be, well, there are other analogous conserved quantities that you can invoke, like in general relativity. There are more complex conserved quantities that are analogous to energy in that case. But energy is such an abstract concept. Think about what it is: kinetic energy, half mv squared. Okay, gravitational potential energy. Okay, gm m over r. Okay, these are mathematical quantities that happen to be they happen to all add up to the same thing, but there's nothing necessarily fundamental about the concept of energy, although we have come to believe it and to feel that there's something so fundamental. Okay, so that's point of view number one. Point of view number two is that energy is actually conserved in the expanding universe, and the addition of new dark energy and the loss of energy from redshifted photons is offset by the fact that as the universe gets bigger, it acquires more and more negative gravitational potential energy. Okay, and so if energy can be negative, then it's possible to add positive energy. Now, this doesn't sound very intuitive because you could just infinitely create an enormous amount of mass if you're allowed to continually borrow infinitely from this well of negative gravitational potential energy. Okay, which of these is right? Possibly both are reasonable ways to look at it. I kind of prefer the first description, just because I think it's good for us to not be stuck in our ideas of what is fundamental, including potentially the conservation of energy. Okay, so Michael also talked about conservation laws in black holes. Now, black holes conserve energy because they grow in mass when they swallow things. They conserve angular momentum and charge because they acquire those properties when they swallow things with those properties. The issue, I think, for things like particle physics, things like baryon number, okay, so the number of protons, neutrons can be changed, but more importantly, quantum information. Okay, so when black holes were first conceived, and it became clear that that quantum information may be destroyed, in particular when Stephen Hawking realized that black holes must radiate, and the radiation produced by black holes would be this totally random thermal glow, okay, of radiation, which should contain none of the information of anything that fell into the black hole before it, and that should continue to happen until the black hole evaporates into a puff of energy, and all of the quantum information that went in before should be gone. Now, this, if anything is fundamental that should be conserved, it is quantum information. And the reason is that quantum mechanics really, really depends on the on this one concept, on conservation of quantum information. Of course, we've done episodes on it. Now, we think we now know that, in fact, black holes may actually conserve quantum information, even through their Hawking radiation. And to answer why, I'm going to read the question from Bob Dead. I hope you're okay, Bob. Which is that when mass is just above the event horizon of a black hole, is the event horizon slightly distorted due to the effects of the extra matter? How is that related? Well, Bob Dead in that question just solved the black hole information paradox, because that is exactly the proposal that Gerard 't Hooft, who I mentioned earlier for his cellular automata, came up with to save the conservation of quantum information in black holes. The idea being that in a black hole, when things fall in, they slightly distort the gravitational field at the event horizon at the location where they fell in. Okay, so for someone exterior to the black hole, what they see is this kind of frozen imprint on the event horizon where things fell through. And in reality, they don't see things fall through. They just see objects falling and becoming frozen in time. And that ultimately manifests as a distortions in the gravitational field at the event horizon. And those distortions then influence the Hawking radiation that that black hole later emits, and can give to that Hawking radiation the quantum information of the infalling objects. And so the Hawking radiation should therefore carry out that quantum information. Okay, so well done, Bob. You solved the quantum information paradox a couple of decades late. And by the way, the whole idea that you can have this information printed on the exterior of the black hole is what started the whole holographic principle, which Leonard Susskind then came in and gave a full sort of string theoretic description to, and showed us that, holy crap, it may be that the whole universe is such an information imprinted on a surface. 1 second, guys. I'm going to let you guys hang out with our friend for a minute while I do this. Guys, this is Simone the cat. She made a brief appearance in the comment responses a couple of episodes ago. Many of you are asking to meet her. We'll introduce you properly. Simone loves to watch the pigeons out the window, landing on the fire escape. She's also a huge fan of treats. Well, no, she's too distracted right now by you lot. Okay, thank you for sitting through that short commercial break. We're back live. I hope Simone entertained you. Just as an example of some of the challenges that we go through, filming every episode these days, just down the street there's a fire station. And so particularly in these troubled times, the sounds of New York in emergency cut off our recording of essentially every paragraph. And so we have to go back to the start and record again. That and the garbage trucks. But, you know, it's the price of living in the big pandemic-ridden city, I guess. Okay, so, you know, one thing that I thought this would be a cool opportunity to do would be to talk about some of the stuff that we're all doing in these difficult times. You know, I've been mostly stuck in this apartment. I've been running a lot more because we're allowed to go running. But I'm interested in what you guys are up to, whether you have tips for getting through quarantine if you are indeed locked down like we are. Please let us know. It's not so bad. Say hi to everyone, Simone. All right, so while you're typing those comments, I'm going to show you around a little bit, not too much, because most of this apartment is this giant hoarder's trash heap. It's mostly floor-to-ceiling toilet paper rolls, hand sanitizer, and just bags of refuse. That's a joke. We have 3 rolls of toilet paper. I'm actually slightly worried. But I do want to show you a couple of things, okay? You've met Simone. Mostly I want to show you what I'm reading right now. Okay, some of this, you get a lot more time to read when the outside world is deadly. Okay, so, well, first up, while we're here, a number of you, many of you have commented on this piece of art. Okay, it's a beautiful time to see it because the sun shines off the gold leaf. But what is it? Where did it come from? Well, I'm pleased to say that it was created by my partner, whose name is Bahar, and I would actually love it if she would come and say hi to you all. So the artist in residence.
Well, I'm just bringing Simone. Oh, wait.
Hey everyone, this is Bahar and Simone. Simone is shy.
Oh.
She's never had such a large audience before, but
Oh, say hi. They're friends.
It's all right. You get used to the camera. Maybe Simone can go away just for the moment. Okay, so this is Bahar. Bahar created this amazing piece of art. Okay, and so my own artistic taste was finding the right person, the right woman, and by chance this came with it. But people are quite curious about this piece. What can you tell them?
Oh well, it's the galaxy.
It's the galaxy.
I'm playing to the crowd. But oh, it is gold leaf, and gold was forged in some supernova.
Well,
or emerging of neutrinos.
Neutrons. See, You learn a lot living in Shea, Matt, and Bahar. So it's gold leaf painted with a variety of inks, and indeed gold. We used to think it was forged in the hearts of the most massive stars before they, well, as they exploded collapsed and exploded as supernovae. But recent findings, in particular, watching that one merging neutron star pair that followed that gravitational wave signal, indicated that in fact gold may be forged in the mergers of neutron stars, as many of the heavy elements and many of the elements in your body. Okay, so we have.
Except that this is not real gold. This is copper and zinc.
What? What? All this time? The lies. It's stunning. Maybe we'll see more of Bahar's art. Now, Bahar is only incidentally a great artist. She's also a science writer, and I actually thought that maybe she could help answer a question that you all had, or that someone had. Can I find that real quick? Well, the question was, what is my favorite science fact? And the fact that our asker, whose name I can't locate while I'm holding this laptop up, their favorite science fact was about how radio-controlled, I'm guessing planes, can do a flip in the air, and how it's all about the conservation of angular momentum. Well, it so happens.
So this is about the cat. Oh, okay. So this is about the cat. Cats always falling on their feet, no matter how you throw them. We could demonstrate that, but we're not gonna drop Simone. But yeah, that it's been actually a huge mystery for over 300 years. Well, how cat can turn themselves midair without violating the conservation of angular momentum. And you want me to explain?
Well,
how?
so Bahar wrote a New York Times article on this very topic. It's the print edition, so you can't look it up unless you're also hoarders and have a stack of New York Times. But you can give us a sense
or
of.
you could do an episode.
Okay, so I'm going to do.
This is not a trivial question. It's been it kind of stumped scientists for over at least 300 years.
But not just any scientists.
No, like people like James Clerk Maxwell. They tried to figure out how cats flip midair without pushing in against anything, without an internal engine.
Literally by dropping cats, by the way.
Yeah. Apparently there was a rumor about him at Trinity that he drops cats out the window. And apparently that's not true according to him. He only dropped them 2 inches off the table, trying to see how quickly they can do it. And they can do it 2 inches up. They can still rotate enough.
That's incredible.
But how can a free-falling body, rotate itself midair?
Do you want to tell us?
It can do it in vacuum. It can do it in outer space.
There are some amazing videos of astronauts trying to drop cats in, like in the International Space Station or whatever. There are.
Oh yes, those from the is the Army, the Air Force experiments in the 60s.
Very important research.
In zero-G
Very
flights.
important research. So
it wasn't in outer space. It was in zero-G flights. Yeah.
So I do need to do an episode on that, but the answer is really cool, and it's especially cool because we don't actually know for sure. There are just some proposals, but it's pretty nifty.
Yeah. Well, essentially, what it comes down to, I mean, there are a lot of details, and there's no like complete consensus on how this happens, but it does not violate conservation of angular momentum, obviously.
I mean, cats are magic, but
not in this case. But what they do is that they're not a rigid body, so they divide their body in 2 parts by bending their backbone and rotate them with stretching the arms and legs in the right combination, so that in the end it all adds up, doesn't violate anything. It's perfectly legal as far as physics is concerned. But it is a very interesting question.
And cool enough that it really warrants a full graphics team to be on it.
Yeah, yeah.
So stand by for that.
I'm gonna leave you with.
Okay, thank you, Bahar. Everyone, thank Bahar. Okay, so beautiful art. I'm very lucky, both mostly for Bahar, but also for the art. Here's another piece right here that's in the works. This one has some amazing patinas on the copper. It's going to be incredible. I mean, it is incredible already. Actually, I want her to be done with it because we can hang it. So I have telescopes. This is a little show and tell while we're on our way to the books, by the way. This is a lamp. I call it the Eye of Sauron because it's extremely like ominous, and we rarely turn it on because it's a little bit scary. Here we have a solar telescope. Okay, so this is a 6 centimeter aperture solar telescope. Its main job is to block light out rather than let it in. It's only through a tiny wavelength band from an emission line, hydrogen alpha, I think it is, in the upper atmosphere of the sun. So you see these incredible details of the sun's structure. You can see the convection cells where plasma is bubbling up from below the interior of the sun. You see the sunspots, of course. You see prominences on the edge where giant streamers of plasma are channeled by magnetic fields. It's a cool toy. Now, but what have I actually been doing during the lockdown? Well, this thing here is, it's a block of concrete because there wasn't enough concrete jungle outside. It's a coffee table, and I made that. It's actually super dodgy. It's made of wood we had lying around the house. Then coated with this kind of concrete surfacing material. I mean, it actually is concrete, but we didn't actually have to pour a full thing of concrete. That's a drawer. It's a concrete block with a drawer. I know, incredible. Inside the drawer, there will be a projector. There's going to be a speaker built into it, game console, all of this cool stuff, hopefully. I've become very attached to my apartment during this time, and I just really feel the need to do things that aren't just sitting at my computer. Okay, so trying to build crap. We try to fill the place with a lot of plants because it makes us feel a little less trapped. Here is another telescope. Now, this is a little bit difficult to see in the light here, but this is a rather large telescope. Okay, so it's a 10-inch Dobsonian. You can see the rings of Saturn are amazing with that telescope. It's also a plant holder, by the way. I bet you didn't realize, but telescopes make amazing plant holders. Okay, back here we have a little reading nook. Okay, that funny shaped thing is one of Simone's little homes around the house. Okay, piles of books, some read, some not read. For the moment, what I'm going to do is place you all on top of the telescope. It also makes a fantastic laptop holder as well as a plant holder. Okay, so right here, and there we go. We have some books. Okay, so the main, I guess, motivation for this bookshelf is books that we're either reading right now and really into, or that we want people to think that we're reading right now and are really into. That's a joke. We actually do our best to read this stuff, but there's also some much dorkier stuff that we wouldn't put here. Okay, so there's a lot here. The worst book by far is my PhD thesis, The Host Galaxies of Radio Loud Active Galactic Nuclei. I think it's only been read by the 3 examiners. My mother, I don't think my advisor even read it, actually. But that's a... Oh. Bahar asks who I got it signed by, and the answer to that, if I can find that chapter, maybe I'll ask you to find that chapter while I...
Oh, it's in the beginning. Or maybe in the end.
while I get back to the other thing. So Bahar is a neuroscientist by training, okay, science writer by profession, and so more of her stuff is here: Principles of Neural Science, Kandel, Schwartz, Jessel, Classic. Okay, there's some Oliver Sacks here, so more brain stuff. This one I love, and I assume that this is on everyone's bookshelf. This is Malformed Forgotten Brains of the Texas State Mental Hospital. Okay, obviously an academic classic. It's just full of beautiful, beautiful malformed brains of different types. It's the ultimate coffee table piece. This is a topical one right now, Poached. Okay, so this is on the world of wildlife trafficking, and clearly we are now seeing the consequences of wildlife trafficking, which is that we have these emergent diseases which were safe in their reservoirs among different species like bats or pangolins, but brought out of these remote places into human populations and then infect us, and very likely the COVID-19 coronavirus came from such a reservoir, so poached. The books that I'm actually reading now or read very frequently, I just put here for you guys. Really, the coolest thing here, I think, is this book by Roger Penrose. Okay, so The Road to Reality. It is not a light read. Now, a number of you asked in the questions some questions about pursuing a career as a scientist, a physicist, or an astrophysicist, and many of you talked about how the math is daunting, or even just asked what level of math you need. So, to quote Roger Penrose, "We cannot get any deep understanding of the laws that govern the physical world without entering the world of mathematics." Blah, blah, blah. Skipping forward. "In modern physics, one cannot avoid facing up to the subtleties of such sophisticated mathematics. It is for that reason that I have spent the first 16 chapters of this work on the description of mathematical ideas." So this is a book. This is like Roger Penrose's ultimate, this is how the universe works. And he honestly spends the first 16 chapters just giving you the background math. So for anyone who wants the background math, but isn't about to start a college degree, Roger Penrose, The Road to Reality, the first 16 chapters would actually give you the grounding, not by themselves, but they would show you what you need, and you could go from there and direct perhaps your own study to get the grounding you need to understand relativity, gauge theory, all of this super mathematical stuff. Okay, so that's the answer to your question. Roger Penrose's first 16 chapters. All right. So Roger Penrose is one of my favorite all-time ever scientists. Another favorite all-time ever scientist is this guy, Paul Dirac. He's just so amazing. So this is Paul Dirac's biography, The Strangest Man, by Graham Farmello, and just the number of anecdotes about Paul Dirac. So in Cambridge, that there was a thing that Dirac stories were a thing. Everyone had a Dirac story for some of their encounters with Paul Dirac. As an example, when he first met the young Richard Feynman, he it was at like a cocktail party, and it was a super awkward conversation because Paul Dirac was not the most verbose of all scientists. He was very physicist-y. Okay, it was said of Paul Dirac that that he would not say one word when 0 words would do. There was also a unit of measurement in Cambridge for the rate of speech, where 1 Dirac equaled 1 word per hour. So when Feynman comes up to him, is like, okay, awkward silence, and then Paul Dirac says, I have an equation. Do you have one too? Yeah, so Paul Dirac had the Dirac equation, which basically brought together all of quantum theory in the was it 1929 or thereabouts, predicted the existence of antimatter, and eventually ushered in quantum field theory. Yeah, he's amazing. The theorist's theorist, they call him. Einstein would always carry around his version of Paul Dirac's textbook on quantum mechanics. And so when Einstein wanted to address a problem in quantum mechanics, he would be known to say, where's my Dirac? Okay, Paul Dirac. So I'm an astrophysicist technically, but I've had to learn a lot of quantum physics for this show. I mean, I learned it, right? I learned it in graduate school, but then didn't apply it for quite a while, and so really had to come back to it. I love my Sakurai, okay, which is a lovely treatment. It's a little advanced, but the place that I started was this thing here, Messiah Quantum Mechanics. I wish I'd started with Paul Dirac's book, but that's where I started. That requires a bit of math too, but if you've read the first 16 chapters of Penrose, you should be fine. A book that's really close to my heart professionally is this thing, Astrophysics in a Nutshell. Okay, Dan Mowes. So it's a graduate level book, but it's insanely accessible for anyone who's okay with algebra and relatively basic calculus. Okay, and you can see that it's very well worn. I have 3 copies of this for all of the different places that I might want it, and it's just a beautiful, beautiful like exposition of how we can derive the physical rules that govern astrophysical events. It's awesome. Okay. Hawking and Penrose, The Nature of Space and Time, somewhat pretentious title. It's an okay read. This is one that I really recommend to all of you. This is very chewed up because, this is Bahar's copy actually, and she got me onto this. But this is Werner Heisenberg. So this publication is called Physics and Beyond, but the original is called Part and the Whole, or something like that. But Heisenberg is such. He was a close friend of Paul Dirac, but he's quite the opposite in personality. He's very warm and bright and poetic and philosophical. And the story of how he came up with, I mean, he invented quantum mechanics. He did it. His stuff came before Schrodinger by a few months, but he's a savant. So I recommend Physics and Beyond by Werner Heisenberg. It's the story of his life also, and what it was like in those times when some of these great ideas were emerging. It's in general good to not just read what modern people talk about this stuff. So there's a good book by Einstein called Relativity. It's varyingly a delightful read and extremely dry. And Einstein actually says that he's not going to add unnecessary flour flourish or poetry to it, because he wants it to be principally extremely clear. And so if you want to, if you're down for that, going to the original source is a great idea. I kind of just put this one up here because it was lying around, the anthropic cosmological principle. Now, this isn't, we talked a lot about the cosmological principle recently, and this is not your go-to source. This is a book that came out later that kind of, I think, misinterpreted the original ideas about the cosmological, about the anthropic principle. Okay, the idea that the universe that when we try to understand the universe that we see around us, we have to take into account that it must support observers like us. Okay, there is an unavoidable observer bias in the universe that we observe. Okay, and so I mean, there's some interesting stuff in there anyway, and this is just there because we were talking about it, the black hole war. Okay, Leonard Susskind had this famous bet with Stephen Hawking that about the conservation of quantum information. Hawking thought that quantum information would be destroyed in a black hole. Susskind thought that it would not, that there'd be a way to save it. And ultimately, Hawking, of course, ceded the bet and agreed that the quantum information could be preserved. Okay, those are some books. I asked you guys to let me know what you guys are up to during these harsh times. I'm going to take us back to our studio. Over here, I'm carefully avoiding our piles of hoarded toilet tissue. Framing is really everything in this game. So what I'm doing, I'm reading, I'm building a concrete coffee table, I'm working on this crazy clock puzzle that's one day going to be this cool wooden clock. It's taking us a very long time to do it. And drinking Negronis. What are you guys doing? Okay. Music. So I'm going to have my lovely assistant read me a few of these, if that's okay. Blacksmithing? Damn, now I'm jealous. Just learning film stuff here. Video games, especially space ones. Video games. We're going to build a console into this coffee table. I was originally planning to build a touch screen like into the center of it, so it could be all board games at once. And then I realized that was just like too tech bro nerd. I should just build a coffee table first and then get to that stuff later. Learning code, planting, growing vegetables. Writing a piano concerto? Wow. Okay, so building a forge? Man. I was like so excited to impress you guys with this stuff, but writing fancy novels? Okay, all right, impressive, impressive. I think, let's see how we're doing. I think we're gonna just answer a couple more questions and then we'll wrap up our first live stream. We're already an hour and 10 minutes in. Okay, 1 second. Okay, so a few more questions from the live feed right here. Now, I didn't choose these. Bahar chose them for me. And so this is going to be a fun game in which we see if I can answer things without any preparation. I mean, I didn't really have preparation for the previous ones, but I at least chose ones. So in general relativity and quantum mechanics, so Trevor asks, both require observers. Why does science not take into account the observer as a fundamental part of reality? Well, I think Brandon Carter, who was, I think, the original guy, the astrophysicist who came up with the anthropic principle, would say that we must take the observer into account in the sense of the type of universe that we observe. I think that John von Neumann and Eugene Wigner would say that the observer is essential because they collapse the quantum wave function when a measurement is made. And both von Neumann and Wigner seemed adherents to this idea. I believe that later on, Wigner was less convinced that the observer had to be a particularly essential part, or that the act of observation didn't have to be conscious. However, so I think, you know, the answer to the question is that some people want the very act of observation to be fundamental. I'm not convinced. You know, I think that something exists without the observer, whether it bears any resemblance to how our brains process and construct that reality, you know, to present us with an image is highly debatable, and certainly it's not completely so. The real universe is very different to what we imagine it to be. But even if we didn't exist, I think something would be there. So now we're getting down to the interpretations of quantum mechanics, and the Wigner von Neumann interpretation requires an observer. You know, of course, both the de Broglie-Bohm and the pilot wave, and also Everett's many worlds, do not require an observer. Observers are just emergent, properties. Although our particular location in either the universe or the quantum multiverse defines what we see, and so is very important to take into account. Yeah, I mean, it's a super interesting question, and I think it comes down to really some of the most fundamental questions about, what is anything? Okay, so another one. Okay, so Charles Mortarif asks, if time reversed direction for a while and then resumed, how would we even know it happened? Wouldn't everyone's memory of those moments be unremembered? So I think that's a nice way to put it. If time reversed and went forward again, what would the effect be? In a deterministic universe, where every instant relies entirely on the previous instant, for example, in one of these cellular automata universes, then rewinding it is just perfectly reversing those steps, which will then proceed perfectly exactly as they did their first pass through. And certainly nothing would be remembered, and we wouldn't perceive anything from it. But that gets to a real kind of philosophical question, what is time, blah, blah. I think we'll do some more episodes on that. But what it would even mean to reverse time, if you think in terms of what's called block time, that the dimensions of space and the dimensions of time, in a sense, just all exist. Space-time exists from the beginning of the universe to the end. And we, as observers of the universe, are kind of just like traces, world lines through that block time. Our conscious experience is just what happens when you trace a super complex path of many, of the patterns of the particles that make up our bodies through this four-dimensional block space-time. And so time moving forward, does time move forward or backwards? Maybe not. Maybe this thing exists, but our conscious experience is just a trace through that. I also like to think of it in terms of playing a record. Okay, so on a record, you guys remember records, CDs, whatever? Okay, the songs are there, imprinted in the grooves of the record. and they're always there, and the whole song is there. But the melody only emerges when you play the record in a certain direction. Okay, you might then ask, what is the needle of that record? Well, I think the analogy breaks down there. But so in a sense, passing to answer the question more succinctly, rewinding and then going forward again may not actually have meaning. Okay, that time just is. Okay. So in the last minutes, well, first of all, to wrap up the science, there are two questions/comments that I feel I must. First of all, Ben L asks, "Hi Matt, hi Ben. Where do the fundamental laws of nature come from?" Thanks, Ben. I can't tell you that. That's obviously something we're saving for the last episode of Space Time. In however long it's going to take us to get there, you're going to have to wait. Okay, it's going to be more than Penrose's 16 chapters. Where do the fundamental laws of nature come from? I'm hoping we can keep making space-time long enough that someone figures it out before we have to stop. And one of my favorite questions, I can't find it, maybe I'll find it later. So the last thing, I guess, then, is to talk about what to do going forward. And this was, I'm inspired to think about this by Charles Copley's question, which is that he said, we need to know, what is my favorite incarnation of the Doctor? Doctor Who, that is. And so, what do we do going forward? Well, we watch a lot of shows. Some of you came up with shows that you're watching in the chat, or I'll mention a couple that we are watching. So I'm inspired by this question about Doctor Who, and I will answer it because of the following. So we started watching this show called Devs, D-E-V-S, and it's an amazing show. It's about this tech genius who builds a quantum computer that does something that I can't tell you what it does, but it involves a lot of cool talk about the interpretations of quantum mechanics. Is it de Broglie-Bohm? Is it Everett's many worlds? And it's a fun watch. It's very cool. So this is a show by Alex Garland, and I got onto it because our quantum physicist Graham Gossell sent me a link to an interview in which Alex Garland is talking about his inspirations for the show, and he starts saying, "Oh, and there's this. I think he's an Australian guy. He has a beard." And then they showed a clip of Space Time. So apparently, Alex Garland watches Space Time, and maybe got some of his, I don't know. Anyway, it was very touching. So Devs, maybe we played a small part that some of the science in it is quite good. There are really good discussions about determinism in quantum mechanics, and the different interpretations of quantum mechanics. He took some liberties, as you must, but I would recommend giving it a watch. The reason, though, I bring this up is that although it passed some time, we found it kind of dark. Okay, it's quite an ominous show. I can't say more, but we realized that these were the early days of the lockdown, and we needed something uplifting. And it was like, what is uplifting? Doctor Who. Doctor Who is the ultimate, hope-bringing series. Okay, the Doctor himself is, such a cheerleader for humanity, and it's some of the episodes are so-so. Some of the episodes are amazing, but we found ourselves uplifted. And after watching season 6, that's Matt Smith of Doctor Who, we found we could go back and finish watching Devs. Okay, so to answer your question, my favorite Doctor, well, I grew up with Tom Baker. Okay, that ages me. I'm a Gen X, sorry. But I always thought no one could ever beat Tom Baker. He's so crazy, he's so colorful, and none of the Doctors after him ever came close until David Tennant. Okay, to me, David Tennant really, Tom Baker is a genius. He's very goofy though, but David Tennant really brought the Doctor to a new level, and so he'll always be the best Doctor to me. But I didn't have great hope for Matt Smith, but after watching season 6, he's like maybe my equal second with Tom Baker. And I can't even tell now if Tom Baker is just because, I grew up with him. I also think Jodie Whittaker did a fantastic job. I think she was hampered by the writing of her series, unfortunately. The writing in a lot of David Tennant's and a lot of Matt Smith's is just superb. Okay, so the other thing that we're watching and that I strongly recommend is a little show called Midnight Gospel. Okay, so write that down. It's by what's his name? By Pendleton Ward, who you know him from Adventure Time, obviously. So it's very Adventure Time-y in its animation and very science fiction-y. So it feels like you're watching a science fiction show, except for the fact that I don't want to give away too much, but it is deeply profound, and it really blew both of us away. We watched it very quickly, and I think we'll watch it again. It's artistically amazing. So Midnight Gospel. So I know you guys have been peppering the chat with your own recommendations, and I'm going to go through those, and because now we're actually done with Midnight Gospel, we're done with Devs. I think hopefully you'll generate some more distractions for us. Oh yeah, Tales from the Loop. Tales from the Loop is the other one. Excuse my vanishing for a minute, but Tales from the Loop is this show. It's so great, but it's based on the art of this artist, Steinman Stalenhag, The Electric State, and the vibe of it is the vibe of The Electric State. Check out Tales from the Loop. Okay, so if anyone hasn't watched that. All right. So this has been a delight. I feel like I'm not stuck in my apartment eternally. So many great suggestions here. So I had enough fun that I would love to do this again sometime. Maybe we see some more of my place. Maybe one day we do it at one of your guys' places. I don't know. But thank you so much for joining. We'll keep making the show. And now that we've realized that the past and future may be good, but the present is actually a really cool place to hang out. I hope to see you in the present again real soon. So to end, as always, stay safe and blah, blah, space time.